Hey guys, Mr. Backerberg here. In this video, we're going to look at discontinuous integrable functions. So we've got a theorem that guarantees that all continuous functions are integrable, but some functions that have discontinuities are also integrable. A bounded function that has a finite number of points of discontinuity on a specific interval from a to b will still be integrable on that interval if it's continuous everywhere else. The function could even be undefined at a specific point of discontinuity. We would just exclude that one value when we're doing our Riemann sum approximation. So as we're taking a look at this first example, we're going to try to integrate the function, the absolute value of x over x. Now that is a discontinuous function in here. Because we've got a fraction, x is not allowed to be 0. But as we're doing this integration, we're going to be running from -1 to 2. So we do have some sort of issue happening around 0. But because our function is continuous everywhere else except for that specific x value, we can still do our integration. Now, if we were to graph this out, we'd actually end up with a couple of horizontal lines. Now, to do this integration with these horizontal lines, we're actually going to look at areas of rectangles in here. So our starting x value is right here at -1. Now, we're going between this horizontal line and our x-axis. So we're really looking at this chunk of stuff in here. Now, on that right-hand side of our horizontal line, we can't actually use 0 because it's undefined in the function, but we are infinitely approaching that value of 0. So if we look at this horizontal distance for our rectangle, we're starting at -1, and we're infinitely approaching a value of 0. So basically, the length of that rectangle is 1. And as far as the height in here, well, we're doing the absolute value of x divided by x. Well, this y value down here is at -1. So we're going down one space as well. So if we do the area, 1 times 1, we get an area of just 1. Now that's below the x-axis, so it's actually a negative area. So that first chunk gives me an area of -1. And I want to add on the area of the chunk that's above the x-axis. Well, we're going out to the x value of 2, so if I draw in the rectangle there at 2, and again, getting infinitely close to 0, again, we've got a height of 1 in here, so we've got this length of approximately 2, with a height of 1, so that gives us an area of 2. So if we add that area of 2 onto that area of -1 from earlier, then we get a final answer of 1, for the integration of this function. Taking a look at this example, we're going to look at integrating another discontinuous function. So we've got x squared minus 4 over x minus 2. Now this fraction is actually reducible. On top, we've got a difference of squares. So that's going to factor into x plus 2 and x minus 2. So when we do that, that's going to allow us to cancel out that x minus 2 on top and on bottom. So we end up simplifying this down to just x plus 2. But because our initial function was a fraction, we need to be concerned about 0 happening on the bottom. So in this case, x is not allowed to be 2, even though we cancel out that factor as we're simplifying down this function. X is still not allowed to be 2 because our initial function was that fraction. Now, we're doing this integration from 0 to 3, so we do have to be careful about that undefined value happening at 2. But if we were to graph this new function out, it's just going to be a straight line, but because x is not allowed to be 2, there's technically a hole in the picture at the x value of 2. Our calculator just doesn't do a very good job of showing that hole in the graph. Now, as we're looking at doing this integration, we're going to use areas just like we did in the previous example. So we're going from 0 to 3, but there's something bad happening at 2. Well, so starting at that x value of 0, that's going to be right here, we're going until we hit that bad value at 2, and we're looking at the area in here. So that's going to be a trapezoid, and then from that bad value of 2, we're making another trapezoid going out to the x value of 3. Now, what's happening as we approach this value of 2 from either side? We're infinitely approaching 2. So these two trapezoids get so close together that we end up essentially not leaving any piece of it out. The chunk that we would end up leaving out essentially has a width of 0 since it's happening at just one point along this line. So we're not really excluding any actual area from our final answer. So because these trapezoids keep getting closer and closer together, infinitely close together, I'm not even going to worry about excluding anything from the actual area of this trapezoid. Now, as we're looking at finding the area of a trapezoid, to find the area of a trapezoid, the formula is 1/2 times base 1 plus base 2 times the height of the trapezoid. Now, this trapezoid is technically laying on its side. The bases need to be parallel to each other. So this vertical piece right here is actually our base 1, and this vertical piece over here is our base 2. So we're doing 1/2 times the length of base 1. Well, that's a height of 2 spaces, so that's going to be 2, plus the height of our base 2 value. Well, that's going up to 5, so I'm going to fill that in for my base 2 value. Now, the height of the trapezoid, since this is laying on its side, we actually want to look at this distance going across the bottom here. We're going from 0 to 3, so that distance is actually 3. Well, if I take 2 plus 5, that's going to be 7. So I have to do 1/2 times 7 times 3. Half of 7 is 3.5. 3.5 times 3 gives us an area of 10.5. So again, even though we were technically splitting one specific value out of there, it didn't really affect the area because the width of that chunk is essentially 0. There's nothing that needs to get left out of this actual area calculation when we're doing the integrating. One last example we're looking at here. This is a greatest integer function, and we're going to integrate that from 0 to 5. Now, if we graph this one out, remember the greatest integer function gives you all of these flat horizontal chunks between consecutive integers. So we're going to do the integration using areas again. Well, as we look at this first horizontal chunk, it essentially has a length of 1. It's going from 0 and it keeps getting infinitely closer to 1. So it's got a length of 1, but there is no actual height to this rectangle in here. So that's going to contribute an area of 0. But then if I look at this second rectangle where we jump up, now we've got some actual height in here. So we're going to be able to do some area calculations. Again, this length is infinitely approaching 1 unit long. But now we've also got a height of 1 unit, so 1 times 1 is going to contribute an area of 1 for that rectangle. As we look at the next piece over and draw in that rectangle, that's now got a height of 2 with a length of 1, so 1 times 2 is 2. Now there is technically just a very little gap between these, but similar to what we looked at in the last example with that trapezoid, that gap is so small that we essentially don't end up leaving out any area values in our calculation. Same thing over here as we're looking at this piece. Again, we've got this rectangle drawn in. Now we've got a height of 3 with a length of 1. So 1 times 3, that's got an area of 3. And then we've got one more chunk that we're going to have to look at because we're going out to that x value of 5. So if I look at drawing in that rectangle, now this one's got a height of 4 with a width of 1. So that's got an area of 4. So if we add up all of those individual areas, 0 plus 1 plus 2 plus 3 plus 4, that's going to give us an area of 10 units for our integration. Again, we don't have to worry about these gaps between the rectangles because they're so infinitely small that we don't have to worry about leaving any actual area out. That's going to be it for this video. Thanks for watching.